Hello students, Dr. Shragi here, and I'm going to walk you through what's going to be the last lecture of Module 4, where we're going to be talking about working with pairs of data, where we have two simultaneous or corresponding observations of different properties, and we have a lot of sets of these. We have n sets of these observations, so they work in pairs. We'll see lots of examples of paired data in this module. All of the descriptive statistics that we have seen so far in this module have been applying to single random variables. What was the average solar flux on our panel? What was the average power what was the average electrical load and things like that? They were just replying to a particular single random variable. Whereas now we're going to turn to pairs of random variables, which can help us understand how the two random variables are going to be related to each other. What we're going to be doing is taking samples of two different random variables and then making sure that those observations match up. So if we have one random variable called like x and another random variable called y, then we need to make sure that observation xi matches up to observation yi. I need to be comparing, let's say, the cloud cover now to the output of my solar panel now, not mismatching those observations. I want to make sure that, and then tomorrow's observation of cloud cover matches up to tomorrow's output from my solar panel, and so on. Now, we're going to be visualizing a lot of these kinds of relationships using scatter plots, where we take each pair of observations and we map them to a point where one observation goes on the x-axis and the other part of the pair goes onto the y-axis. In other words, each spot on the diagram corresponds to one ordered pair of observations. And I'm going to have a couple of different of these sets of these observations that we're going to be using throughout the whole lecture today. One is going to be what I'm going to call the direct relationship, where we're having kind of a pattern to our observations. Here I have 9 observations, where on the x-axis I just made up some data for cloud cover, in terms of like a fraction. And on this case, on the y-axis, I have the long wave down. Remember, long wave radiation coming down from the sky depends on things like the greenhouse gases and the cloud cover in the sky. The cloudier it is, the more long wave radiation those clouds are emitting and coming down to the surface of the Earth. And so we have some kind of set of 9, n equals 9 pairs of observations here, and each one of them maps to a spot on our scatter plot. Okay, so we can kind of see how there's sort of an upward trend here in this data. I will also sometimes be using this one that I'm calling the indirect relationship, where here I have another scatter diagram. Again, I kept the x-axis is, again, observations of cloud cover in terms of the fraction of the sky, whereas the y-axis now is going to be power generated by like a solar panel or something like that in terms of watts per square meter of panel area. And so again, this time now, of course, as the cloudier it gets, the less power we're generating. So you see this sort of downward trend, right? Where when it's not very cloudy, we generate lots of power, and when it's very cloudy, we generate hardly any at all. And finally, I'm going to have this other example where I have n equals 9 observations, where there's no real relationship between the data at all. Here I'm making it, again, cloud cover in terms of a fraction on the x-axis, versus simultaneous observations of the electrical load on the grid at that particular residence or something like that. I didn't really think through very much what I wanted those that to be exactly, but I had this idea that probably the cloud cover is not very related to how much electrical demand there is. So these points don't really fit any pattern. There's no trend or anything like that going on here. There's no real relationship between these data. This set of 3 different ways, this direct relationship, this indirect relationship, and this no relationship data set will be seen throughout this very large set of PowerPoint slides. So if I just turn to my direct relationship one, I want to illustrate a couple of interesting things that we can see on this particular data set. Let's see how these the points on this scatter diagram are related to x bar. So x is our first column of data here. It's the cloud cover in terms of fraction. And if I added those 9 values up and divided by 9, I get x bar is equal to 0.4278. And so I'm going to plot that value on the graph right there. You can see how it's a vertical line centered at 0.4278, and that's our x bar. And see how all of the observations are somewhat different. All of the x observations are somewhat different. None of them are exactly 0.4278. So there's always some little difference between the values of x at time I and x bar, which we can illustrate with these little, these little line segments here that connect our observations on the x-axis to the to the value of x bar. So like I have a big long line up there near the top that is corresponds to observation x3 minus x bar, is that fairly longish line up there at the top. You can see we also have, like I have illustrated there, x9 minus x bar, that's its distance from x bar, x4 minus x bar, and so on. The right term for these are the anomalies. Every one of those observations, the difference between the observation and the average is called an anomaly. And so I've just highlighted the anomalies here. And I could have done the same thing if I go back to my basic diagram here. This is again still those same 9 points on a scatter plot associated with the direct relationship. If I did the same sort of thing for the y data, I mean, I could have taken what's in my y column there, and I could have added those 9 values up and divided by 9, and I would have gotten y bar, which happens to be 388.9. And I could show that graphically on my scatter plot by putting a horizontal line that corresponds to y bar equals 388.9 on the y-axis there. And you can see how we have little line segments that connect the y values on our scatter plot to the y-axis right there, and those little lengths there correspond to the y anomalies. You can see farthest to the left there I've got y7 minus y bar highlighted. That's the distance between that particular observation, y7, and the average. It's y7's anomaly. Or you can see I did the same thing there for y3, just to illustrate that guy over there. y3 minus y bar is that large anomaly over here on the right side of the diagram. So we have this idea that we have these anomalies with respect to the axes here. But now what I want to do here is instead, on my scatter diagram, I have drawn on here a horizontal line that represents y bar, and I have drawn on here a vertical line that represents x bar. But then for one of my points, the one farthest into the top right corner of my diagram there, I've actually drawn its x anomaly and its y anomaly there. So like that little line segment right there that goes from the horizontal line up to our point, that's y3 minus y bar. And that little line segment that goes from our x bar over to our point is x3 minus x bar. See, I've made a little rectangle here using its height being y3 minus y bar and its width being x3 minus x bar. Well, that little rectangle that I just created there is it's a little rectangle, and it has an area. That little rectangle there has an area of the quantity x3 minus x bar times the quantity y3 minus y bar. That is the area of that little rectangle on the diagram there that is described by how big the anomaly is in the x direction and how big the anomaly is in the y direction. Now, as it happens, that particular point has a positive x anomaly and a positive y anomaly, so x3 minus x bar times y3 minus y bar is a positive number. That area of that rectangle right there is positive. In contrast, I could take a different point on my diagram. I'm just going to pick this one that's down there kind of in the lower left. And again, I still have a vertical line there showing my value of the x bar, and I have a horizontal line there showing my value of y bar. And I've drawn two little line segments there that show the anomalies for, as it happens, 0.7. So that is y7 minus y bar is its how far the point is from the y bar. And x7 minus x bar shows us how far we are from x bar right there. And once again, those two little points there have carved off a little rectangle. And that area of that green rectangle that's on there is the quantity x7 minus x bar minus y7 minus y bar. I'm sorry, x7 minus x bar times the quantity y7 minus y bar. Oh, my bars are missing on the, okay, it's x bar and y bar. Now, because both x7 minus x bar and y7 minus y bar happen to be negative in this particular case, a negative times a negative is a positive, so the area of that rectangle there is positive. We could, for just as a point of illustration here, take another point. I'm going to take this point that's kind of in the bottom right corner of the diagram now. And at that point, again, I have a vertical line drawing there and there to show x bar, and I have a horizontal line on there showing y bar, and I have these line segments that connect our point to those lines, illustrating x9 minus x bar and y9 minus y bar. And just as before, those two little anomalies carve off a little rectangle there, which I've colored in pink. And the area of that little pink rectangle is x9 minus x bar, I apologize, a bar seems to be missing on the slide, times the quantity y9 minus y bar. Okay, now, x9 minus x bar is a positive anomaly. We're to the right of the x bar. But y9 minus y bar is a negative number because we are below that y bar. So one anomaly was positive and the other anomaly was negative. So the product of those two anomalies is actually a negative number. That little area there of that pink box is actually a negative area. In fact, we could divide up our scatter diagram here into 4 quadrants. And any observation of those, any of those little spots on our scatter diagram here, on our scatter plot, any of them that land in the pink areas are going to be corresponding to negative products or negative areas of the rectangles that they describe. And any observation that corresponds to locations in the green quadrants correspond to a product of anomalies or an area of a rectangle or whatever that's positive. So we have 2 of these pink quadrants that correspond to negative products of anomalies, and we have 2 quadrants drawn in here in green that correspond to places where the product of the anomalies will be positive. Now for a direct relationship like the one that I'm illustrating right here, notice that there are more data points in the green areas than there are in the pink areas. There are more positive products of anomalies than there are negative products of anomalies. Wouldn't have to be that way. For example, if I took this indirect relationship we had before, where we kind of have that downward trend to the data, well, here, if I put in an axis that is x bar and another axis in there that's y bar, and I divide the area of the scatter diagram up into 4 corresponding parts, you see that there are more negative products than there are positive products. Okay? This is going to help us get to the ways that we can describe how these data sets are related. And for that matter, I mean, if I took this no relationship case right here, and again computed x bar and y bar, and divided my scatter diagram up into 4 quadrants, well, you can see that we have about the same number of positive products as we do the number of negative products. We have about the same number of points in the green areas as we do in the pink areas. Okay. I mean, I want to do more than just like count how many of these observations fell in each of those 4 quadrants. I'd really like a way to quantify this because I think that probably big rectangles should be more important than little rectangles and so on. Another way to think about this would be to actually numerically put it as this equation that I have here on the slide here, where I'm saying, see the products of the anomalies there? xi minus x bar times the quantity yi minus y bar. That is the area of the rectangle associated with point I. And we're just going to sum up all those areas of those rectangles from I equals 1 to n, where there are n pairs of data. Well, for this case of there being no relationship, these numbers are going to add up and it's going to be basically 0. Okay? Whereas, for example, for a direct relationship, where there are more values that are in the positive areas, the green ones, than there are in the pink areas, which are negative, that value of that summation of xi minus x bar times yi over y minus y bar is going to be a positive number. In the same way, for the indirect relationship, there's going to be more of those negative products than there are positive products, so that sum of the products will be a negative number. This is actually pretty slick, and this gives us a way to define a number that we're going to call the covariance. The covariance is written COV, and then the 2 variables, the 2 random variables that we are trying to understand the relationship between. So in this case, it's covariance of x comma y is equal to, well, basically this is just that sum of squares over there on the right-hand side. It's the sum of the, I'm sorry, not sum of squares, the sum of those products. Same exact thing, except now I'm dividing by n minus 1. Okay, cool. Okay, so basically we built up this idea of which quadrant the point falls in, the observation falls in, should tell us something about how the nature of the relationship between the 2 random variables are, led us to this idea of covariance, where covariance is going to be a number that describes the nature of the relationship between the 2 data sets. So for example, for the direct relationship, I actually crunched the math, and it turns out the covariance is 43.8. Notice I'm not giving you any units or anything like that yet. For the indirect relationship, as it happens, the covariance works out to negative 46.9. Okay? And for this one with no relationship, I get, whoa, negative 20. Well, I was kind of hoping to get 0. Wonder how I ended up with something that I mean, it's still got some covariance. Gosh, I wonder how I'm supposed to know if negative 20, is that a lot of covariance? Is that is that so little I don't need to worry about it? How am I going to figure all that stuff out? Covariance is a really interesting value. One thing, what in the world are the units of this thing? Well, as it happens, you could work through and actually figure it out, and the units of the covariance are kind of peculiar. Whatever the units are of your your first random variable, and then whatever the units are of your y, your second random variable, covariance has units of the two kinds of units multiplied by each other. So like when I was comparing the electrical load on in the house to cloud cover, my units were in fraction times kilowatts. Or when I was comparing the cloud cover to the amount of solar power generated in watts per square meter, my units were fraction times watts per square meter. These are awkward units. They hardly make any sense at all. What is the range of covariance? Well, it turns out covariance can be anything. There is no, I know you're thinking already in terms of some things that we're going to see later that are like, they range from -1 to 1, or they range from -100 to 100. There is no range to covariance. It can be whatever it needs to be. Much like the, variance can be whatever it needs to be, or standard deviation can be what it just depends on how much spread there is in the data and so on. This is kind of frustrating. Here's another kind of difficult point. Is covariance a statistic or a parameter? Okay, strictly speaking, what we're computing here, because it is a function of the sample, this is the end observations that we sampled, this would actually be a statistic. And strictly speaking, the statistic of covariance is sample covariance. And then, in fact, there is a real property called covariance that is a parameter of the relationship between the two data sets. And that's pretty important in kind of a philosophical way. In practice, except for a few very strange places on the internet where I found people who had scanned in entire stats textbooks and so on, no one ever really worries about the difference between parameter and statistics when it comes to covariance. We can use the words sample covariance and covariance basically synonymously, where they refer to a property of the sample. We took a sample of data and from that we computed the covariance. I suppose strictly speaking it is the sample covariance, but that is not terminology that is very standard. But now if I think about this slide that I just saw, boy, there was a lot of unattractive features of covariance. Covariance had a nifty, kind of vaguely intuitive way of thinking about it, of this idea about where the points fall on the, what quadrant of a scatter diagram they fall in and so on. That's kind of a nifty idea, but man, covariance has a lot of problems. The units are a mess. I don't have any. Congratulations, your covariance is 46. Is that high? Is that low? How do we test it? How do we know if that's enough? That's all a really big mess. Sure would be nice if we could get past some of these problems and come up with a measure that was unitless, so I didn't have to worry anymore about all these crazy units of my descriptions of paired data sets, and had a fixed range that I could actually understand. Like, we are ranging from -1 to 1 or something like that. And of course there is a statistic that can do such things. It's called the correlation. Sometimes called the Pearson Correlation, sometimes called the ordinary correlation. Okay, it turns out there's actually a number of different ways you can define a correlation statistic. But the one that your book is using, by far the most standard one, the one that you get in Excel if you type equals correlation, is the Pearson Correlation, or the ordinary correlation. It is a measure of how well two random variables fit a relationship, especially how they fit a line. How well do they match up with each other? Now, the actual definition here of Pearson's correlation is not such a hard thing at first. The symbol for a Pearson correlation is R, with the two random variables that we're correlating written in subscripts. So like if we were correlating a random variable called x and another random variable called y, then a correlation between the two is just R of x, y. And at first, the actual definition is pretty straightforward. It's just the covariance of x over, comma y divided by the standard deviation of x and the standard deviation of y. It's actually, notice the sample standard deviation and the of x and the sample standard deviation of y. It's s's, not sigmas. Okay, that's not so bad. Oh, then you start expanding these bad boys. And you take the covariance, you put in the equation we had for covariance into the numerator of that function, and then you put in the equation that we had for sample standard deviation of x, and then you put in the equation we had for sample standard deviation of y, and oh my goodness, it starts getting to be a big mess, and it doesn't get much better. Because, okay, you can get that 1 divided by n minus 1 out of there with a little bit of algebra, but it doesn't get a ton better. Now, there's actually a lot of different ways to write this correlation. It can be, rewritten a couple of different ways, but they all come out to be equivalent to this. A not trivial thing to compute, but it's not the end of the world, and we'll have tools that will help us with this in things like Octave and so on. Now, there are a lot of advantages to correlation, though, the Pearson correlation here. For one thing, it's unitless. No more worrying anymore about whether the weird units, no more difficulties of figuring out how you compare the correlation of power to temperature with the correlation of how you compare cloud cover to temperature or something. I mean, they all have the same units now. They have a fixed range. Correlation is going to range from a -1 to a +1. And the correlation has the nifty feature of being symmetric. The correlation of x and y is the same as the correlation of y and x. All these are going to be properties that are going to be awfully handy at various points in the future. So for example, I can actually take the correlation of these 9 observations in my direct relationship example here, and as it happens I get a correlation as 0.78. Or I could do the same thing for my indirect relationship example here, where again I just fabricated these numbers, but when I actually did compute their correlation, the correlation between these two data sets happens to be -0.894. Okay, I don't know if that's good or that's bad. Well, we can figure that out at some point. And again, for that one that was no relationship, I mean, those plots, I'm not very convinced that there's much of anything going on in that scatter plot diagram, but I'm still getting a correlation here. I'm getting a correlation actually of -0.3. I wonder if that's good or that's bad. I don't know. How do I tell? Well, we don't know that yet. But no matter what, we've got a number of different examples here of different relationships between the data, and we have a wide range of correlations here. From 0.78 for our direct relationship all the way down to almost -0.9 for our indirect relationship, and something that's kind of near zero but not particularly near zero for no relationship. What does all this mean? What do these correlation coefficients mean? I mean, my guess is just your experience of being involved in higher education and working with sciencey, engineering-y kinds of things. You've heard of correlation before. You probably have some idea that like the closer the correlation gets to 1, the stronger the relationship is between the data, whereas the closer it gets to 0, the less relationship there is. As it gets closer to -1, the relationship is getting stronger but in a negative way. Where, you know, there's a downward slope to the data and so on. But what does it mean? How do you make sense of these numbers here? Let's take a look at the situation again with this direct relationship. And what I'm going to do here is I'm going to just with my eyeball sketch in a line. I'm trying to draw a best fit sort of line here that just kind of goes through my data, that describes what's going on, that shows that trend, that shows that pattern. We could draw a line right through our scatter plot. And every observation there is some distance from that line. Now, in a future module, of course, we're actually going to learn how you come up with that line, the slope and so on, its properties, and how you can use that to make estimates and so on. But suffice it to say, the place on that line that is right, it's at the same value of x as your actual values of I, that is called x, that's called y hat. That is your estimate of y. So those little line segments are illustrating the difference between y of I, the actual observation of y, and y hat, what we would predict y to be if we knew this line. We knew that this best fit line was in there. No matter how I draw the line in there, those line segments are not going to exactly be all 0. My line that I sketched through there will never fit all those lines perfectly. There'll always be some distance away from the line that I drew. Let's think about the sum of the squares of those distance, which I wrote there as that little equation. I equals 1 to n, the summation of the squares of those little distances there. Okay, so I've got all those little bars, the little line segments there on that diagram there. Picture them, add them all, square them all and then add them up. Depends on what am I going to get for that number as I sum up the squares of those errors. Well, it depends on how good I was at drawing a best fit line. Here, I drew a terrible best fit line here. Look, we end up with line segments that just have huge values for the sums of squares. All these lines are these lines that connect my best fit line, that is a terrible fit line, to our points there. They're terrible, they're huge. The difference between my estimates of y, my y hats, and my actual observations of y, yi, are terrible. The sums of squares of this is going to be huge. There, this one's terrible too. I've got all these silly, huge line segments. I mean, some of them are not so bad, but most of them are huge. We could also draw best fit lines through here that are not so bad. that have fairly small sums of squares of those differences between y of I and y of I hat. In fact, we could get even better. And the more I wiggle around with this little line segment, my best fit line, I could kind of start getting in there where there were some of the squares of these errors in the estimates are getting smaller and smaller. But in fact, it can be proven that there's exactly one possible best fit line. That's the term, best fit. That line, which is the one I'm showing you right there, for those 9 points there, is the one that minimized the value of the sum of the squares of the errors. The distance between y of I and y hat of I. Oh, okay, so there's just one best fit line. There's just that one place that I could draw that line in there that is best as to where it goes through there. And look what we can do once we have that line. We'll learn in a future unit how you actually come up with that line and so on. But when we are trying to compute, look at what we can do with this best fit line. Well, back when we were computing the variance, what I've done is I've taken our data set and put two copies of it side by side. On the left there, I highlighted y bar and all the distances, the anomalies between y of I and y bar, because that's what you use in order to figure out the anomaly. I'm sorry, the variance, right? It's the sum of the squares of all these little distances, like the one that I have circled in red. Okay, like that one I have circled in red, he's pretty big. He's contributing a lot to the variance of that data set because that little line segment that I have circled in red is going to be big when it's squared, right? So that one's contributing a lot to the total variance of the data set. On the other hand, over there on the right rather, I've now put in the best fit line. Well, once you know that the data set has this pattern to it, well, if we had known that the value of x, the cloud cover, was going to be 0.9, we'd have predicted a value of the long wave down that isn't really all that far from what came up to be the real observed value. In other words, that little error, that little line segment between my best fit line and the actual observation just isn't really all that big. We see that a lot of the variance that was in the original data over there on the left has been explained by the fact that there's this best fit line. Explained is a powerful word in statistics. We are saying that we now have a way, yes, there is variance here, but we know why it is. It's here because of this slope of this best fit line. In this case, an awful lot of the variance associated with that point that I have circled there is explained by the fact that, oh, it's just way out there on the x-axis. When we are out so far on the x-axis, our value of our y hat, the place on that best fit line that we're drawing our line segment to, well, it's not that far. We have explained most of our anomaly here. We have explained the fact that there is some original variance that is actually explained just by the fact that we have this best fit line. Our observation isn't all that weird. I mean, if you looked at that diagram on the left, you might think, wow, that is a really strange observation. He's contributing a lot to the variance. He might even be an outlier. Then when you actually get the best fit line, you say, oh, he's not that strange at all. He's just way out there on the x-axis, but he actually doesn't fall very far off of our best fit line at all. And we could look at other examples as well. For example, look at those on the panel on the left there, those two observations. They're fairly far from our y bar. And so as a consequence, they contribute significantly to the total when we computed the variance. A lot of the variance in that data set comes from just those 2 points. But then on the right, when we actually were able to show what the best fit line is, well heavens, those points are practically right on the line. The difference between those points and the line, the best fit line, is very, very small. We've explained almost all the variance in those points just by drawing in that best fit line. Statisticians love the idea of how much of the total amount of variance is being explained by some process that they've discovered. In this case, this best fit line. We like to describe it as the percent variance explained. How much variance is being explained by this best fit line or whatever. Percent variance explained, PVE, or sometimes written the percent sign, VE. And as it happens for a best fit line and for correlation and so on, astonishingly, the percent variance explained, it's just your correlation R squared. R squared of your two random variables, x and y, is the percent variance explained. Well, you have to multiply it by 100 to get a percent, but you know what I'm saying. Because it'll be a number from 0 to 1, and then you multiply it by 100 to actually get percent variance explained. So you can actually, based on the correlation, square that number and determine from that how much variance in your phenomena is being explained by that relationship between the two sets of data. So for example, for my direct relationship, I had that, remember we had a correlation between these two data sets of 0.78. You take 0.78 and you square it, you get that the percent variance explained is 60.8. In other words, about 61% of the variance in Y is explained by the fact it has this relationship with X. Okay? In the same way, for that indirect relationship, we have a correlation of negative 0.894. You square that, you get right around 80%. 80% of the variance in Y is explained by the relationship it has with X. Okay? That seems pretty convincing. I mean, if you had discovered that there was some connection between X and Y here, and you could explain 80% of the variability in X by what's going on in, 80% of the variability in Y based on what's going on in X, you've made a great forecast tool. What about no relationship? I mean, here we had a situation where we thought the correlation was about negative 0.3, and if you square it, you end up with 9.3%. Not very much of the variance in X is being explained by how it relates to Y here. Okay, now, this stuff about paired data kind of leaves us with more questions than answers. It's a little bit of an awkward place to break the module of the course because I'd like to be able to tell you more about how we're going to use this, how we're going to compute these regression models, and so on. I mean, I haven't yet told you yet how we're even going to come up with that best fit line. It's not something we just sort of eyeball in on a scatter plot. I mean, we could, I suppose, but that's not what we're going to do. I haven't yet told you how we're going to know if it's statistically significant. I mean, even when we had like these correlations, like, okay, one of my correlations was about 0.79, another was like negative 0.3. I'm willing to say that one is more highly correlated than the other, but is one sufficiently low, is the correlation low enough that I don't need to care about it anymore, things like that. Statistical significance is something we're coming to in a later module. We're not going to worry about that right now. Kind of wish we could, but we can't. How are we going to use this information that comes to us from working with paired data to start building a statistical model? That's of course where we're heading in a class called Modeling Electrical Load and Yield, right? Is we're trying to come up with an idea about how we're going to use these tools to build a different kind of model, in this case a statistical model, to be doing things like predicting how much power load there's going to be or how much production of power is going to be by this wind turbine or something like that. But that's all for the future. Let's save that for future modules. I think after the big project in Module 3, everybody's exhausted. Let's just get through Module 4 and learn a little bit about descriptive statistics and then move on. Okay, before we move on though, I do have a handful of questions for you to help you check to see if you've been understanding what's been going on in this lecture. Alright, question 8. Suppose I measured the cloud cover on 10 separate days, and then I measured the power production by my panel on 10 additional days. I would expect the covariance of these two data samples to be A positive, B negative, or C, trick question, it would not be appropriate to compute the covariance of these two data samples. Oh, this is a hard question in some ways. Alright, follow one of the links below this video to come up to see if your answer is right, and we'll get some feedback.